So to solve a system of linear equations in 3 variables and 3 equations, well, let's think about what we did last week. We solved a system of linear equations in 2 variables that involve 2 equations. The only thing that's different about today's lesson compared to the lessons last week is one more equation. So all the skills that we've learned, elimination, get the equations lined up, get the variables to have the same and opposite coefficient, all of those still apply. It's just you have a bigger problem. So I'm not going to go through the whole logic of why it works. We did that last week. Let's just go ahead and see how the problem changes when I add a third variable and third equation. Spoiler alert, it doesn't change too much. So let's take a look at an example here. Suppose I ask you to solve 4x plus y plus z equals 5, 3x plus 3y minus 2z equals 22, and x minus 2y minus z equals 3. That is a doozy of a problem. Thank you. All right. Just so we're speaking the same language, I'm just going to call the top equation equation 1, the middle equation equation 2, the third equation equation 3. I know it's a very complicated system, but that's the system I'm going to go with. Right. So here's sort of the way you would do it using this elimination method. Again, there's lots of different methods out there, but this is the one I'll be showing. So step 1. Choose any 2 equations and eliminate at least one variable. I put the at least in parentheses because sometimes we get lucky and we eliminate 2 variables, 3 variables, but at the ultimate goal is just to get at least one variable. So just to prove to you guys that there's absolutely a bajillion different avenues we can take, you guys are in control. I didn't pre-plan this. I have not done this example yet. You guys are in control. So step 1, choose any 2 equations, 1, 2, or 3. 1 and 3 I heard. Sorry, he beat you to it. So I'm just going to write down equation 1, equation 3. And again, for emphasis, there is absolutely no rhyme or reason why we chose it. We can literally choose any 2 equations. So we're going to perform elimination as we did last week. When it comes to elimination, you, as the mathematician, have to make a choice. Do you want to eliminate the x, the y's, the z's? It does not matter. Z's are already set up for us, so z might be a smart choice to do. If you chose to eliminate x's, it's not wrong. You'll get the same answer in the end. If you chose to eliminate y's, you're not wrong. You'll get the same answer in the end. But in this case, z's are already set up for us, so it might be the smarter path to take. So I'll just go ahead and add these 2 equations as is. And you get 5x minus y. The z's cancel out, and you get 8. Okay. Unlike last week, when we did elimination, it gave us an equation to solve for a variable. But gosh darn it, when I did elimination here, it gave me an equation with 2 variables. I still can't solve it. He's not useless to us, but there's nothing left I can do with this equation. So what I want to do is I want to save this guy, right? So put it in the back of our minds. We're going to ignore him for now, but we're going to save him. I'm going to move on to my next step. So we're going to put the pause on that step, go into step 2, pick a different pair of equations and eliminate the same, that's important here, eliminate the same variable as step 1. In step 1, you had the choice. You had all the power in the world. You can eliminate any variable you want. For step 2, in order to use elimination successfully to solve the system, you really should eliminate the same variable as you did before. So pick a different pair. So we did 1 and 3 the first time. Take a look at the system. 1 and 2 are here. Why did we pick 1 and 2? Well, that's because that's what the class asked. Doesn't really matter. So 4x, you guys are going to have to read it out to me. 4x plus y plus z equals 5. What's the third one?
3x plus 3y.
3y. Oh, the second one, yeah. 3x plus 3y
minus 2z
minus 2z
equals 22.
equals 22. Okay, so that's the first and the second equation. Now, even if I had another variable that's set up for me, since this is the second step, we are forced to eliminate the z's because that's what we eliminated the first time. So refresh our memories from last week. You focus on just the z's. You don't have to circle it. I'm going to erase it. You want those numbers to be equal and opposite. Currently, they are not the same number, so I have to find the least common multiple. There's a 1 here, so LCM, least common multiple of 1 and 2, is just 2. So the bottom equation already has a 2 in front of the z, so I'm not going to really do anything to him. He stays the same. I hope everyone can see that it's not a big stretch of the imagination. We need to multiply the top equation by 2, right? I'm going to do one extra thought process and go, I want the z's, in this case, because we're limiting the z's, I want the z's to be opposite. Notice how the top z is positive, the bottom z is negative. That is good. So I don't need to use any extra negatives. If they were both positive or both negative, I'd be multiplying by an extra negative. But in this case, we're good to go. So multiplying the top equation by 2 gives me 8x plus 2y plus 2z equals 10. Now it's set up for us. Just go ahead and add these two equations. So we have 11x's plus 5y's. The z's are gone, equals 32. And just like before, there's really not much I can do with this guy. Yeah, you guys can see that. So I'm going to save him. All right. Step 3. If we played our cards right and did step 1 and step 2 properly, what you can do is put your two saved equations together to form a new system. And this system should look a bit more familiar to us that will allow us to solve him completely. Right? So my yellow saved equation was 5x minus y equals 8. My blue saved equation was 11x plus 5y equals 32. Hey, that looks familiar. That looks like problems we did last week. So step 3 is a completely new problem. I'm going to scroll all the way up. I'll scroll back down. This original problem, this original example here, in our minds no longer exists. We're purely focusing on this example, which we did plenty of. That's all we did last week. I hope we can solve this pretty easy. So solve it by whatever you want. Elimination, substitution, I don't care. This should be the easy peasy example. Is it okay if I fast forward through the solving here? Okay, so I'm gonna use elimination because that's what I like, but I'm gonna sort of just go a bit faster here. I'm gonna eliminate the y's. That means I need to multiply the top equation by a 5. So that's 25x minus 5y equals 80, or 40, excuse me. The bottom equation is, the y is already a 5, so I leave them alone. Then I'm going to go ahead and add these two equations. So 25x plus 11x is 36x. Negative 5y plus 5y cancels out. And that gives me a 72. Divide both sides by 36, gives me x equals 2. A common mistake I get is once kids get down to this part, they go, Mr. Vo, where do I plug this in? Or they take this x equals 2, they try to plug it into the original problem and go, hey, Mr. Vo, I can't solve it yet. Mathematically, it's not wrong to plug into these equations. It's not wrong mathematically. It's just it won't help you solve the full system because you have too many variables. So that's why I told you, hey, you are ignoring the original problem. When you get to step 3, this is your new problem you're focusing on. So the answers to those questions, hey, Mr. Vo, I got x equals 2. Where do I plug it in? It is this system that we're solving. So it's those equations that you plug it into, right? So you should never have to ask, hey, Mr. Vo, where does this go? Where does that go? Just plug it into the system you're working with. My rule of thumb is, if you have a numerical answer, see how x equals 2 is a numerical answer? If you ever forget where you plug stuff in, this is the rule of thumb. You always want to plug it into an equation that has one more variable than answers you have. How many numerical answers do I have here? Just one. So I'm going to plug it into an equation that has 2 variables. If I had 2 numerical answers, I'd plug into the equation that has 3 variables. And then if we went bigger, if I had 4 numerical answers, plug into 5 variables, so on and so forth. Right. So I'll take this guy, plug into any of the original equations. It doesn't matter. I'll plug into the top one because it looks simple. But plug into the bottom one if you feel adventurous. 5 times 2 minus y equals 8. 10 minus y equals 8. Subtracting the 10, negative y equals negative 2. Divide out the negative, y equals 2. Our step 3 system had x's and y's. I have numerical answers for x and y's. Technically, I have solved the system. So then the last step, because we're not done yet, because that was not our original problem. Step 4. Substitute your 2 numerical results into any of your original equations. Hey, we might understand this better if we were paying attention, not goofing off back there. So you guys have the luxury of having your paper in front of you. I sort of forgot what the original equations are, so I'm going to have to scroll up to look at it. But we have 2 numerical answers. X equals 2. I'll star him. He's not our final answer, but I'll star him. Y equals 2. So you go up to your original equations 1, 2, and 3. Just pick one. It doesn't matter. I think she beat you out just by a hair. So I heard 3 first. Plug into 1. You should get the same answer. But I heard 3, which was x. You don't have to read out to me.
X minus 2y.
2y minus z. 3. Okay. So we had x equals 2, y equals 2. Just plug it in. 2 minus 2 times 2 minus z equals 3. And then you just do math. So that's going to be 2 minus 4 is negative 2. Add the 2 over. Negative z equals 5. Divide up the negative. Z equals negative 5. Remember how last week I said, hey guys, solving systems, you're finding intersection points. The same thing is true for 3-variable systems, so you should write your answer as an ordered triple. Don't leave it as x equals y equals z equals. Hey, how do we write coordinates if there's more than 2 variables, or if I use a's, b's, and c's? The rule of thumb is alphabetical order. So since I'm using x, y, z's, it should be x, comma, y, comma, z. So your answer is x, comma, y, comma, z. That is how you solve a system of 3 equations, 3 variables. Conceptually, the skills is identical to what we did last week. The only difference is you have 3 equations. Well, you have 3 extra steps. That is the only thing that's different. Question?
So if we were going to graph this, if we have a 3D thing, because that's what the z-axis is, we could.
So the question was, if you guys had to graph this, you would need a 3D thing because the z-axis is 3D. The answer is yes. If you were to graph these equations, you would not get lines, but you would get planes, like sheets of papers. So that's why I'm not going to make you do solving these systems by graphing, because that'd be a pain in the butt to do. We'll just do it algebraically. Yeah.
That's why I thought, the z-axis is a graph. That's cool.
You guys okay with that?
Yeah.
I did want to do one extra example with you guys, because it's going to look funky, and I can bet money that you're going to go, oh, Mr. Vo, this looks weird. How do we do this? So let's just get it out of the way and take a look at it. Suppose I ask you to solve x plus 3z equals 2. Negative x minus 5y plus z equals 1. And 2x plus 3y plus z equals negative 3. Again, just so we're speaking the same language, this is equation 1, equation 2, equation 3. Obviously, what's different about this system compared to the previous example? What equation looks pretty weird?
Yeah, the first one.
The first one, equation 1, looks weird because it's missing a y. Let's take a look at the previous example here. Steps 2 and steps 1 were sort of the setup steps. Picking two equations, doing elimination, saving the equation. We did that because your ultimate goal when you're solving a system is to go back to last week. Last week was nice, safe, warm, and fuzzy. Last week was equations with two variables. That's your ultimate goal. In this example, equation number 1, it gave us an equation with two variables. So in this case, you don't have to do this, but I suggest it because it'll save you half the work. In this example, I'm going to go ahead and save first equation because it's already what I want, an equation with two variables. So in this case, I'm going to save this guy. So step 1 is sort of done for us. So we'll move on to step 2. Pick another pair of equations. Well, if I save the first one, you guys see how we're sort of forced to use equations 2 and 3. So I'll write down equations 2 and 3. Now, if we're making the choice to save equation 1, and you guys told me that equation 1 was missing a y, when I do this step here, I do not have a choice. We must eliminate the y's because you want the variables to match up. So although the z's look nice to eliminate, I would not eliminate the z's in this step because the act of saving the first equation forces our hand to eliminate the y's. Does that logic make sense to everyone?
Yeah.
All right, so let's go ahead and eliminate the y's. I got a negative 5 and a 3. They're not the same. LCM is 15. So the first equation needs a 3. The second equation needs a 5. They're already opposites, so I don't need any extra negatives. Negative 3x minus 15y plus 3z equals 3. So here we have 10x plus 15y plus 5z equals negative 15. Go ahead and add these two equations. That's 7x, the y's eliminate, plus 8z equals negative 12. So that's our blue save. Once we have a yellow save and a blue save, you put them together. Well, it would be a green if we were like to squish them together, but we're just going to put them on top of each other. They're going to stay yellow and blue. And then you just go back to last week. This is a nice, warm, fuzzy problem. Two equations, two variables. Hopefully, we're a little bit better at it. So solve it by whatever method you want. I'm going to use elimination. I'm going to eliminate the x's. So the top equation needs a negative 7. Do note, I multiply by negative 7 because I want one to be positive, one to be negative. That gives us a negative 7x minus 21z equals negative 14. The bottom equation stays the same. I'm waiting. Did I make a mistake somewhere? No. You're good? Okay. And then just go ahead and add these two equations together. The x's are gone. That's a negative 13z. That's a negative 26. Divide both sides by negative 13. You get z equals positive 2. I have one number, z equals 2. So that means when I plug it back in, I need to plug into an equation that has two variables. So that means I plug into one of these guys here. I'll plug into the top equation because the numbers look smaller. So here's the top equation. Plug the z into the equation. That gives me x plus 6 equals 2. Subtract the 6. X equals negative 4. I now have two numbers, so I'll be plugging it into an equation that has three variables. You always want to plug into an equation that has one more variables than you do numbers. Well, that means I need one of the original equations. Now, in the original equations, I'll scroll it back down. Only equation 2 and equation 3 have three variables, so I got to plug into one of them. It doesn't matter which one. 2. I heard 2 first. Sorry. So you're going to have to read it off to me. Equation 2 is negative x
minus 5y
minus y
plus z equals 1.
z equals 1. Right. So plug in the numbers that we have. We have a negative 4 minus 5 times y plus 2 equals 1. And then you just go ahead and do math. So that's a positive 4. So that's a negative 5y plus 6 equals 1. Subtract the 6. Negative 5y equals negative 5. So y equals 1. Write your answer as an ordered triple in alphabetical order. X, comma, y, comma, z. That's your answer. So the moral of the story is these problems look big and scary. And I'll admit, they're pretty big, pretty long. But they shouldn't be scary. It's just an application of what we did last week, just on a grander scale. And trust me, how would you solve 4 equations, 4 variables? Do the same thing, but longer. How do we solve 5 equations with 5 variables? Do the same thing, but longer. We're only going to stop at 3. I'm not going to make you do 4, because that'd be way, way too much. The last thing I want to talk about are special cases. Last week, we ran into some special answers, no solution, infinitely many. Those special cases exist in 3 variables as well. But the good news is it's the same trigger. It's the same thing we're looking at. So last week, we saw if you end up with a false statement. Let me say this. If at any point in time you're solving, if all variables cancel out. Right. So it doesn't matter if it's on step 1 or step 5. If at any time all your variables cancel out, you can stop. Right. If you get a false statement, for example, 0 equals 5, 2 equals 7. If you get something that's not true, the answer is no solution. But if you get a true statement, for example, 0 equals 0, 12 equals 12, something that is true, the answer is infinitely many. Right. So the special cases of last week are the same special cases this week, but you only get a special case if all of the variables cancel out. If you have still just one variable left in the equation, it's not a special case. You got to keep solving. But the moment all the variables cancel out, stop. You're done. You just have one of these 2 cases here, depending on if your result is true or false. Does anyone really need to see an example of that? I did have it prepared. All right, let's just do one really quickly, and then hopefully you can see the idea here. Suppose, now spoiler alert, it's going to be a special case, so you guys already know what the answer is. Well, actually, it's 50-50 guess. Suppose I ask you to solve x plus 2y minus 3z equals 1, 2x minus y plus z equals 3, 3x plus 11y minus 16z equals 1. You guys are in control. Pick 2 equations. 3 and 2 I heard. 2x minus y plus z equals 3. 3x plus 11y minus 16z equals 1. Once you pick 2 equations, you are in control. Decide a variable to eliminate. Y's I heard. So hopefully it doesn't take a lot of thinking to know that you need to multiply the top equation by 11. The bottom equation can stay the same. 22x minus 11y plus 11z equals 33. 3x plus 11y minus 16z equals 1. So that's 25x, y's are gone, minus 5z equals 34. I'm going to save him. Start over. Any two equations?
1 and 2.
1 and 2 I heard. X plus 2y minus 3z equals 1. 2x minus y plus z equals 3. The second time we do this, we do not have a choice. We are forced to eliminate the y's. Hopefully it doesn't take a lot of thinking. Bottom equation by 2. First equation can stay by itself. X plus 2y minus 3z equals 1. 4x minus 2y plus 2z equals 6. 5x, y's are gone, minus z equals 7. Save. Put my two saved equations together. 25x minus 5y equals 34. 5x minus z. It's not a 5y, it's a 5z, sorry. 5x minus z equals 7. And start the process all over again. Eliminate any variable. Want to eliminate the z's? So bottom equation by a negative 5. Is everyone okay with that? So top equation, 25x minus 5z equals 34. Bottom equation, negative 25x plus 5z equals negative 35. Add them together. Wait a minute. X's are gone. Z's are gone. So I have absolutely nothing. All of my variables have canceled out. So that means I need to read what's left over. 34 with a negative 35 is negative 1. 0 equals negative 1. I have ran out of variables. They all canceled out. That doesn't make sense. 0 doesn't equal negative 1. So you can stop where you are. You don't have to do steps 3, 4, and 5. Immediately, it's no solution. Because this is false. In this case, the cancelization happened on step 3. Sometimes it may happen on step 2. Sometimes it may happen on step 1. It doesn't matter where in the process you are. The moment all the variables cancel out, you can immediately stop. It's either going to be one of those two special cases. Okie dokie? Right. So that's it. You guys are doing high-level linear algebra, very complex math. All it is elimination 3 times over. So that is 3.3. I want you guys to